Okay. So, any questions so far? Do you follow what dynamic programming is? Do you know? Do you see exactly where things are going out here? Okay, good. Okay. So, before I get into things, let us just make sure that we know all the complexities of the algorithms we have described so far. So, we have Dijkstra, assuming that you have positive edges. What is the time complexity of Dijkstra? Remember what happened? You had a priority queue, you kept popping, and every time you relax some number of edges, and you know that sum total you relaxed E edges, which was E decrease keys, and you popped V times. So, it was V log V plus E log. Agreed? So, the log V's are essentially the percolation up to your priority queue. You did exactly E relaxations, which corresponded to E decrease keys. Each decrease key goes log V, okay, which essentially was that. Then we did Bellman fold, which allows negative edges. And this turned out to be order what? V times E, or in other formulation, if you have the whole thing sitting in a matrix, V, this became a V square, that became VQ. Okay, so, this is the current situation that we have. Now, the last time I introduced to you a dynamic programming technique, it did not look like it was doing much at all. Okay, so, you can actually look at the entire thing from a very different point of view, which was essentially Bellman fold, which said just keep relaxing all edges, do it V minus V times, and I gave you a proof which did not touch upon anything which is dynamic programming like. I now ask you the following problem. So, now that we have done single source shortest path, if we were to take on the problem of all pairs shortest path, in fact, the Google map is not a single source shortest path problem, because Google map goes about storing all pair shortest paths. Okay. Google map does not know where you live, and so when you ask it a query, it is from some source node to some destination node. So, in your graph V, you do not have a very specific node called the source node. You have every node could be a source node, every node could be a destination node. You need all pair shortest paths. How would you solve this problem? If I were to ask you, knowing what you know so far, to do an all pair shortest path, you would just run through all your source nodes, right? That is a trivial, obvious solution. So, the all pair shortest path that we know of already is essentially Dijkstra multiplied by every node becoming your source node. You repeatedly do Dijkstra from every node, you will get a shortest path from that. Okay. So, for every pair of nodes, you are going to solve your shortest path problem. So, that is your all pair shortest path solution. What you will have then is that multiplied by V. Or if you have negative edges, assuming you do not have negative cycles, you could again do all pair shortest path, and you would get Bellman fold times the number of vertices, which would give you order V square E or order V to the power 4. So, if you went with this, it would be v times c. If you went with this, you would be v times v cube, which is v to the power 4. This is what we know of currently. Assuming that there are negative edges and there are no negative cycles, it turns out that it is not possible to improve upon this trivial extension to Bellman-Ford, which essentially says go and do a shortest path from every source node. But consider what happens when you do not have negative weighted edges. If you do not have negative weighted edges, it looks like the best you could do is Dijkstra done many times. Okay, so, the best thing we could do is v times e times log v. I will now propose to you a genius of a solution which brings that down by log v. Okay. The solution is so beautiful that it actually gets a name. Okay. When you have beautiful algorithms out there which actually chop a substantial portion of the best known complexity so far, you allow yourself to name the algorithm after your known name. So, what we will describe is something called Floyd washer. The assumption once again, like Dijkstra, is that all edges are positive weighted. Okay. So, before I do Floyd washer, let us just look at what Bellman-Ford is like in the case of all pair shortest paths. So, the previous solution I gave you was d I of length at most k was the min of d I k minus 1 and d j k minus 1 plus w j. If I were to take this formulation, which is for the single source shortest path, and try to throw in all pair shortest path, I would just change the indices. Okay. So, my corresponding solution would be I to j of length k is minimum of d I to j of length k minus 1 d I to L of k minus 1 L to j. Okay. All I have done is I have introduced the source as a first index and the destination I left the same. So, previously, because all of these were from a single source, I did not have that index. Right now, I am just putting the S out here. So, the S is here, S is here, S is there, and the S then runs over all possible nodes. So, this is your I, and I. This once again is a recursive solution. You would essentially solve this by just writing loops and building the solution from below. In the previous case, your D's were sitting in that manner, okay, D1, D2, D3 and so on and so forth, which all refer to DS1, S2, and so on and so forth. Now, you would have an array of values. S to S would be 0, I to I would be 0 all along the diagonal. So, you will have values of 0 in the diagonal, everywhere else you would have infinites, and you would essentially build from that d zeros to d 1s and then d 2s and d 3s and so on and so forth. The array will essentially update itself over and over again. The amount of time you would take to go from one array to another would be v square, and there are v square of that many. Sorry, the number of relaxations would be essentially e v square, and you would go essentially V times. But you have that many to fill, so that gives you the V to the power 4. Instead of filling just V elements, you are filling up V square elements. Okay? This index is still the length of path. So, we know that it is all I have done is I have taken Bellman-Ford and simply put a new index on it, which gave me another loop that gives me an additional V. So, that is where I went from order V cube to order V to the power 4. Mind you, dynamic program is all about index. The question is, this thing seems to be extremely costly. V to the power 4 for a graph like even the United States is going to take a long time. We do not like even quadratic. We like linear. Quadratic itself starts feeling bad. This one is V to the power 4. All pair shortest path as coded right now is order V to the power 4. That is way too much. Is there some way we can bring it down? What we are thinking of is, this looks like the only solution you could think of. You have an index, you have come up with your index of length k minus of the length of hops, and then you are using that to do your relaxation. You are essentially doing what Bellman-Ford was doing. The genius of Floyd-Warshall is to say that maybe we can first of all improve upon this. Half the people would not even think, but maybe you could, because you are already seeing that Dijkstra is not V to the power 4. So, the assumption is that you have only positive edges. If you have only positive edges, Dijkstra would give you V, E is again V square here. So, V cube log V. So, if you have positive edges, you should not be doing Bellman-Ford with a loop around it. That brings it down from V to the power 4 to V to the power 3 log V. But it looks like Dijkstra is the best you could do for a single source, and maybe it is the best you can do for multiple sources. Okay? It very carefully relaxes edges. It does the whole thing in a single run of relaxations. It does not relax an edge more than once. And that itself is taking us V cube log V. So, to be able to take out that log V would be a tremendous accomplishment. What we will see is an algorithm which actually takes out for all pairs the log V, ends up with V cube. So, Bellman-Ford is V cube single source shortest path. Floyd-Warshall will turn out to be all pair shortest path also in V cube. And to do that, the genius is essentially to think of some other index. An index that is so unnatural that it actually throws people off completely. An index that nobody would in their right mind even think of. Remember, all dynamic programming, I am telling you, is you should throw the dynamic and programming out of your head and just think about the problem in a way which is essentially a recursive solution. You are looking for a recursive solution. And for a recursive solution, you always need an index. This index was the length of path. The goal here is that so long as you keep the length of path to be the index, you cannot produce an equation any different from this, and this clearly is order V to the power 4. So, the only way we can actually reduce the complexity is if we could change the index. Floyd-Warshall uses the following index. It says, instead of seeing for all pairs the length of path being your index, consider the following very peculiar index. I will allow the lengths of path to be whatever you wish. However, apart from the source and the destination, which are allowed to be all pairs, the intermediate nodes I will only allow to be either node 1 or node 1 or 2 or 1 or 2 or 3 or 1 or 2 or 3 or 4 and so on and so forth. Where are these indices coming from? I have just taken all the nodes and ordered them randomly. I took all the nodes, I said you will be number 1, you will be number 2, you will be number 3, and so on and so forth. Okay. Try to think of this. I have taken my graph, I have put some strange order on the nodes. The nodes were not really ordered at all. I just took all the nodes and I just lined them up and said you will be 1, you will be 2, and so on and so forth. And now I am going to use, based on this, the following very peculiar index. It is going to be I to j, where the path is allowed to be however long you wish it be. I do not care. But dij superscript k is going to stand for the distance from I to j, so that the intermediate nodes, the nodes that you are allowed to pass through, are only 1 through k. You are not allowed to touch any other node. Okay. So, here is my new version of dijk. So, it looks exactly like that, but this k is not length of path. This k is, here is I, here is j, and this path, the intermediate nodes, are only allowed to be between nodes 1 through k. Okay, first steps first. How long do I have to run this for index k in order for me to get the correct answer? Once again V. So long as you are allowed to go through all nodes, you will get the correct answer. So, if I could write a recursive equation for this, once again that recursive equation would start at dij v and would have sub problems that need to be solved, sub problems that need to be solved. That would be my recursive solution. Agreed? So, just like the length of path being at most v, here we have the intermediate nodes being all nodes. It is the same thing. However, and I am going to leave this up there, you will clearly see how this is very different in terms of its recursive solution. So, let us try to figure out what the recursive solution is. I have here I, j, and let us assume that this is dij k. So, all the nodes here are between 1 and k. I am also assuming that the edges are positive weight, because I am trying to fight with Dijkstra being run v many times. I want to write this solution as solutions to sub problems. So, I am going to try to look at what dij k minus 1 is. Dij k minus 1 essentially is the same thing, where you have the shortest path from I to j, but you are not allowed to go through k. You are allowed to go through everybody other than k. Okay. So, it is quite possible that the path from I to j, this value, either goes through k or does not go through k. If it does not go through k, then that is the correct answer. The shortest path from I to j that goes through nodes 1 through k at most, if it turns out not to go through kth node, the node valued k, then it will have it will be the shortest path from I to j, which is allowed to go through 1 through k minus 1, which I already have the solution to. Okay, so, I will need to solve that sub problem, and that is one piece. What is the other possibility? Yeah. It does pass through k. It does. So, either it does not pass through node number k, or it does pass through k. If it does pass through k, can it pass through k twice? can the shortest path from I to j through nodes 1 through k, assuming that all edges are of positive weight, can it be that this shortest path pass through k twice? Goes to k and then goes, and you see again k, what happens? You have come back to k. It is a cycle. There is no possibility that you have a cycle, because all edges are positive weighted, and so cycles are guaranteed to be positive. So, this path, if it does pass through k, will pass through k only once. Okay. What is this subproblem? I am assuming this is the shortest path from I to j. There were two possibilities I looked at. One is it passes through node k, which is this one, does not pass through node k. If it does not pass through node k, this solution is that solution, I j k minus 1, passes through 1 through k minus 1. I am now asking you, if this is the shortest path and it does pass through k, and if I put k there, what would this problem be? Is this a shortest path too? Is it possible that this is not a shortest path? If this were not a shortest path, you would take some other path to get to j. This clearly then is the shortest path from I to k, passing through 1 through k minus 1, right? Because none of these nodes can be k again. If it were k, you would have a cycle. So, all these nodes are 1 through k minus 1, all these nodes are 1 through k minus 1, and so I know what this path is in terms of solutions that I could have stored. This is the genius of Floyd-Warshall. If you do not feel happy listening to this solution, then it is good that you are at algorithms, you take this course, but algorithms is not for you. Okay. The only thing you get out of algorithms is every so often somebody comes up with a solution, you read it. If it is in you, it is tremendous. You get the tremendous high. But even if it is not in you, you see one of these solutions, and if a smile does not come to your face, this is the wrong place. This is all we have, smiles. Okay. So, here is what Floyd-Warshall is then doing. So, dijk, this is a new index k, this index is about going through nodes 1 through k, is once again the minimum of not going through k, so k minus 1. And if you do go through k, then you have to go from I to k using nodes 1 through k minus 1, and then from k to j once again using nodes from k minus 1. This is solving shortest paths all pair. This is solving shortest paths all pair. This is Bellman-Ford run one more time with a loop around. Look at the difference. Why do you think this is better? Look at this. There is an extra index out there. Okay? You run through this index. So, when you are doing this minimization, whereas this minimization is going to go through this index v times, in this particular case k will be fixed. And so, this minimization is essentially the comparison of 3 terms. You take 2 terms in your matrix, you add them up, compare that to another element in your matrix. I have actually taken out a scan through v many nodes in one jump. And all I did was change the index. You can tell this algorithm needs a name. That is why it is called Floyd-Warshall. Okay, so let me write down the code itself. It will look terribly simple. So, Floyd-Warshall is going to run in a clean dynamic programming sense. It is going to take the Wij's to essentially be stored in a big matrix capital W, and it is going to build the Dijk's from that matrix. This is the reason why we usually do not take the last step to tell you what the algorithm basically is. Soon as you have your equation, you essentially code for it. Okay. This is a bottom up solution, it just has 3 loops. It is the ij loop for the pairs of I and j, and the k is a superscript loop. So, you have v here, v here, v here, and essentially at each step you are doing a single thing. So, it is a minimum of one element here. You pick out 2 other elements, add them up, compare, plug it in. On the surface, when you look at an algorithm like this, you cannot tell that genius is hidden behind it. This is Floyd-Warshall. Any questions? So, we have taken care of single source shortest path, all pair shortest path, with the variations being you either have negative edges or you do not have negative edges. If you do not have negative edges, you are supposed to be able to improve things. One improvement was to do Dijkstra many times. That would have given you v cube log v. This one is just log v cube. So, the log v has been shaved off. Yes. It is just looking for the value. Mind you, what I am basically saying is that dynamic programming is all about taking your recursive solution which says k in terms of k minus 1 and flipping it over and saying let me just do k minus 1 or k minus 2. So, let me just do d 0, k equal to 0. From k equal to 0, I will produce k equal to 1. From there, I will produce k equal to 2 and so on and so forth. So, this solution that you are talking about where you would have done a recursive call is actually being stored in the previous array. So, remember d 0 is the solution for 0, and it is obvious that if you are not allowed any nodes as intermediate nodes, then the shortest paths will be the edges themselves. Okay, so, I did not explain this. The reason why the shortest path from I to j, which does not allow any intermediate nodes, is for those that you have edges, there are no intermediate nodes, and so those become the shortest paths, everybody else is infinite. And so, you immediately put the weight vector in there. Edges which do not exist in your graph should have infinite in your weight vector, and it just plugs that in. From then on, you are running just 3 loops where to solve for the capital D k, you are simply looking at capital D k minus 1. So, there is a layer D k minus 1 sitting below you, you are at D k, you want to solve for this position, you go and look at 3 points below. You add 2 of them and compare them with this one, and whoever is the smaller you put there. Okay. It is a constant time complexity. For every location, it is a look at 3 positions in the D matrix below, that is order 1, and so you just have to fill order V square for that level. Next level again order V square, next level order V square, and you do that V times, so V cube. Does that answer your question? This is dynamic programming. That is why you do not have to solve for that. The solution is sitting in the previous level. You have solved from the bottom to the top, instead of writing it recursively where you go top to bottom. Yeah.
Can we say that in general in dynamic programming we sacrifice a little bit of memory so we can improve the
Yes. So, dynamic programming is about balancing out memory with respect to computation. Now, it might turn out that sometime in the future all of this becomes bad simply because memory access itself is much slower than computing it again. But then we will have to change our notion of complexity. Our notion of complexity is that when you are accessing memory, it is order 1. It is not order V cube, but it could be order V cube if you compared real times. It is true that CPUs are getting faster and faster and faster, and memory access is not keeping up. But so long as memory access is approximately not completely out of bounds, this one is a better solution. You put it in memory and you access memory for this solution. You solve it once and put it. But the modern times are about actually not solving and putting it in a hard drive. Okay? You solve on the fly, which goes completely against dynamic programming. And the reason you solve on the fly is simply because your CPUs have gotten so fast that even going and accessing something is much costlier than solving for it again. Good question. Any other questions? Okay. So, when it comes to graphs, I know that it feels like we have been doing graphs and graphs and graphs and graphs. Last topic on graphs. Okay. That does not mean that this is the last topic. I have one more topic on graphs, but that will be it. Okay. So, what we have done so far is traversals. In fact, if you look back, you have not done much really. You have done traversals, you did topological sort and strongly connected components, minimum spanning trees, shortest paths, both single source and all pairs, and finally, we have one more piece. See, in any algorithms course, these have to be touched. And the last piece is flow networks. People have to know about flow networks. So, we will do flow networks. That leaves us a couple of lectures. I am still not sure how I am going to go about it, because I really want to spend enough time with NP hardness so that you fully understand the beauty of the whole field. All that is happening in algorithms right now is on the side of complexity theory and NP hardness and that related things. All of this stuff is already done, put in books. So, very likely after finishing with graphs, I will directly go into NP hardness. If I can manage to finish it in time, I will then come back and do a couple more sundry things. So, these will be unrelated. For example, I will probably do Huffman coding, which is about compression, which is something that you need to know, and longest common subsequences, which is in bioinformatics. If we have time, then we are going to do something in computational geometry. If we do not, we will let that be. Okay. So, the next topic we are going to cover is something called flow networks, and once we are done with flow networks, we will be done with graphs completely, and we will move on. Okay. So, flow networks. The problem is generally described as maximum flow, and the problem essentially is that you are given a graph, and in this particular case you should think of the graph as being either roads with particular capacities like 6-lane roads or 7-lane roads or just 1-lane road, or even better, think of them as pipes with valves on them. Okay. So, it is going to continue to be graphs, they will continue to have weights on the edges, it will continue to be a directed graph, and the edges now, the weights that you are going to put on the edges, instead of it being the length, which sort of is something where you are trying to minimize the length. So, all the problems when you have a length, you are trying to minimize the length. In this particular case, is going to be the capacity, okay, and you want to essentially maximize some kind of a capacity. So, you will once again be given a directed graph, weights on edges. This time the weights will be positive, and they are going to correspond to the capacity of that. So, think of these high weighted edges as being fat pipes that allow you to transfer liquid from this node to that node at much higher rates. We are going to put valves on the pipe simply because we do not want it to be a two-directional pipe. So, for example, you can have something like this. This essentially means that you have a fat pipe going from this node to that node, but you have a rather thin pipe coming from that node to that node. This is very much the case in situations where you have a graph and you have hubs, right. If this were a hub like Chicago, and if you were actually trying to transport material out of Chicago, you would find that the capacity to take stuff from Chicago and send it to some little village out there is much higher than you are being able to take that amount of material from that village and bringing it to Chicago. The reason for that is that your big trains and your big engines are all stored in Chicago. The engines that are stored in small towns are usually smaller engines, their trains turn out to be much smaller, and so this path turns out to be much smaller in capacity than this directed path. The whole idea behind flow networks is to be able to maximize flow from some source node to some sink node. It is a very important problem, once again studied by algorithms people not knowing how they would end up using it, and it turns out that big train companies use these algorithms all the time in order to be able to shunt material from place to place. In fact, they have made it far more complicated because now they have warehouses where stuff goes from one node to another node and can stay in a warehouse. The version of the problem that we are going to look at is if you do not have warehouses at all, and therefore, all the material coming into a particular node has to leave that node that day. Is that making sense? It is the same problem as moving material around this country using CSX or using their rail network. You have capacities on particular edges. The edges are directed, by which we mean that stuff can go much faster maybe from A to B than from B to A. You are usually given a source node and a sink node, and you are asked the following question: how much stuff can you move from this source node to that sink node? What is the maximum amount of stuff you can transfer? Is that making sense? Okay. So, here is the definition of things. So, capacity is essentially going to be put on the link, and so when I say C of U to V, I mean U to V. When I write C V U, I mean V to U. A lot of what we do is just going to be conceptual in the first place, to be able to understand these networks themselves and take the definitions and be very clear about what the definitions mean. So, when I do not have an edge between U to V, what I mean is that the capacity from U to V is 0 and the capacity of V to U is also 0. Okay? That is the case where I take both edges out. If there is a capacity from U to V, but there is no capacity from V to U, then I will not have the second edge, I will only have an edge going in one direction. In all other cases, I will have bidirectional edges between pairs of nodes. Okay? Okay, so, in this domain, this is standard notation. So, S is always the source, T is usually called the sink. So, they will always give you an S and a T. You are supposed to essentially send stuff from the source to the sink. Okay, so, here is an additional assumption, which is that for all vertices in your graph, you should have a path from the source through that node to the sink. Why? You are trying to solve the max flow problem. Assume that you cannot find a path from your source to that node to the sink. I am trying to solve the max path problem, max flow problem. My question to you is, can I take that node out? I look at my graph, it is directed edges. There are some edges that are missing, by which I mean there are some pairs of nodes which do not have directed edges on them. And I find that if I want to go from the source to the sink, all my paths from the source to the sink is not going through this particular node. I do not mean that this node is just sitting on the outside. What I mean is that I might be able to get from the source to that node, but then from that node I cannot get to the sink, or I cannot get from the source to that node. I might be able to get from that node to the sink. If one of these two is the case, does it mean then that when I am solving for the max flow problem, I can disregard that node completely, by which I mean that I take the node out and all the edges going in and coming out? Is there any point in keeping that node? In other words, if I assume that I found a max flow, does that max flow involve stuff going into this node? You cannot go into this node, because if you went into this node, that stuff has to get to your sink. You see, conceptually, this is what we have to figure out slowly. It takes a little time to understand flow networks, because they are so different from the other kind of networks. The ones where you are seeing them as distances and weights being very different from capacities. In a flow network, what is really happening is that any stuff that is getting into a node has to leave. If that node is not connected to your source node, then stuff cannot be getting to it. If stuff cannot be getting to it, from that node only 0 stuff goes to the sink. Okay? If on the other hand, there is no link from that node to the sink, then stuff cannot leave that to get out of the sink, in which case nothing should get into it, because otherwise it will just store up in that particular node. So, what we usually do is you start with a graph and first clean it up. Given a source and a sink, I want to make sure that every node V is actually lying on a path from the source to the sink. If not, I want to take it up. What is the complexity of an algorithm to do this? How would I, given a flow network, find out the set of all nodes such that they lie on a path from the source to the sink? You should be able to solve this problem. Graph traversal. I start with the source, I do a breadth first search, it is going to give me all nodes that you can access. If you want, you can do a depth first search. Okay? The white path theorem tells you that you will be able to get to every node accessible from the source. Store them all on the left side, flip your edges and do the same thing from your sink. This flipping is not the smart flipping of strongly connected components. This flipping is simply to see backward paths. So, take all your edges, flip them over, so that now you can think of the sink as being the source, and now start from the sink and do the same thing, do a DFS. You will get a bunch of nodes. The intersection of these two nodes, these two sets, are the set of nodes which have paths going through them. Okay? So, you take those, take everybody out, you usually get a smaller network, sometimes not, but the assumption is going to be from now on that every node essentially is on a path, on some path. Okay? The bell has rung. It is conceptually something slightly difficult. So, let me come back next time and then take you through the stages. Okay? We will do it next time.